underneath this desk.
Howdy, howdy. This is the second video in 17 plus, dealing with topics that are not in our textbook. And we're going to be talking about here three concepts which are pretty closely related. First, we're going to look at sign diagrams, which is a neat little way to kind of analyze whether a function is positive or negative, whether the function is above or below the x-axis. Similar but very different from that, we're going to look at where functions are increasing and decreasing. Increasing means the functions are getting, their y values are getting higher. Decreasing meaning that their y values are getting lower. Notice that these could be positive or negative. We could have negative y values getting higher or positive y values getting lower. And then we're also going to discuss turning points, which are the places where graphs change directions, where they change from being increasing to decreasing. That special point would be called a maximum. The plural is maxima. Or where they change from decreasing to increasing. That special point would be a minimum, plural minima.
Pro tip, if you want to sound more intelligent while you're talking to people, just include random Latin and Greek phrases, e.g., i.e., minima, maxima, etc.
What is a sign diagram? It's really a simple thing. We're going to have a horizontal line, which is representing the x-axis. Above that horizontal line, we're going to draw pluses wherever our function is above the x-axis, and minuses wherever our function is below the x-axis. Where the function crosses over from negative to positive or positive to negative, we're going to write a 0. And then we're also going to need to be aware of where our function is undefined. There will be two different ways that we could choose to represent that on the sign diagram, and I'll just show you those in examples. Right now, you don't need to know how to graph these functions by hand, or probably any of the functions that we're going to see throughout this video. You need to know how to use your calculator to graph them so you can get a decent picture of them. But I think for everything here, we'll pretend that we are given the graph and we're just drawing the sign diagram based on that. So here's a couple of graphs. Okay? So we look at this first one. Say, well, where is this graph positive? Well, it's positive anywhere to the left of -2 and anywhere to the right of 1. It's negative in between those two. And -2 and 1 are the zeros. So we can draw our sign diagram like this. Now, one way, the way that our book shows the answer, is by just drawing a little vertical segment there. That indicates a 0. That's fine. If you prefer, the way that I learned it in school, the way that I just said to do it a moment ago in the intro, is to draw, like literally write the number 0 there. They're both correct. I don't really care how you do it. All right, looking at this one, it's got 1, 0. They're at 1. And on both sides of that, it's below the x-axis. So this one's going to be -0, negative. Our third example has a vertical asymptote here, right? It's undefined. If we look at the function rule, it does not exist at x equals 0. To the left of 0, it's always negative. To the right of 0, it's always positive. That makes sense when we look at the graph. It also makes sense in the equation, since it would be 4 divided by a negative for any of these values, and 4 divided by a positive for any of these values. The way that the book indicates that it's undefined at x equals 0 is using a dotted line, and that's totally fine. The other thing that you could do is you could literally just write, again, this is what I did when I was in school, I wrote UND for undefined. You want to write the entire word? Cool. Don't care. So we have lots of different options, and I think they're all equally valid and correct. What's really important, though, is that below the horizontal line, we record the special values. The special values are where the function equals 0 and where the function is undefined. And we see that in all these examples. Now I just want to look at some other fun ones. So if we want to draw a sign diagram for this, we're going to draw a horizontal line. We're going to record where the zeros are. Where are the zeros? So it's -2, 1, and 4. How does the sign change as we move from left to right? Well, it goes minus, plus, minus, plus. That's all we need. This one is undefined at -2. It has a 0 at 1/2, and then it's undefined again at 3. How do the signs change? Plus, minus, plus, minus. Sign diagrams are really an easy thing. They are far more useful than you have any clue about right now. They get really, really useful, especially when we get into calculus. So we're introducing the idea here so we can get used to them. They're kind of useful now. They're really useful later. So if you think this is easy, great. Let's embrace that. A little bit harder. So now we have functions, no graphs. Do we need to draw a graph? No, we do not. So here's where the sign diagram is helpful, because now we can get a sense for where the function is positive or negative without having to draw it. Because we have this expression in factored form, which means we can work out really easily, hopefully, where it's equal to 0. This first one should be equal to 0 at -3 and 1. So we're going to mark those two numbers on our sign diagram. It's clearly going to be defined for every value of x because there's no chance of us dividing by 0. And there's no chance of us taking the square root of a negative. So our sign diagram only needs to worry about the two zeros that we just identified. And then if we want to figure out the sign, what we're going to do is we're going to figure out, we're going to substitute just any particular value that's to the left of -3, any particular value that's in between -3 and 1, and any particular value that's bigger than 1. Any values you want. I encourage you to choose easy values. So I would say choose integers. So in the example here, they did x equals 2. Well, if we put in 2 here, we got 5 times 1, which is 5, excuse me. But 5 is a positive number, so we put a plus here. In between the two, I would choose 0. I think that's the obvious choice. That would give us 3 times -1, which is -3. So that's why we have a negative in between there. And if you choose any value to the left of -3, I would choose -4. You'll get -1 times -5, which is +20, so we put a plus. There's a shortcut to this, though. You don't actually have to be concerned with what the answer is. You just need to know what its sign is. So if I choose -4 as my test value to the left of -3, I don't need to know that it's -1 times -5. I just need to say, well, -4 plus 3 is going to be a negative number. -4 minus 1 is going to be a negative number, and a negative times a negative is a positive. We can do the same thing over here. The two zeros are going to be from the factor on the right. That's a little bit easier. We're looking at 3. And then from the factor on the left, that's a little bit harder, but it's going to be -5/2. We don't really care about this 2. It's not really telling us anything about a 0, so we can just totally ignore it. So there's our x-axis with our two zeros. And again, we just choose random points. If we choose 4, which I assume is what they're going to choose here. Oh, they use x equals 5, whatever. Look, it's positive, because 2 is positive, times, this will be a positive number, 2 times 5 plus 5, definitely positive. 3 minus 5, clearly negative. Positive times negative, that's negative. Choose a number in between, 0, positive, positive, positive. It's positive. choose a number to the left of negative 5 over 2. Negative 5 over 2, that's negative 2.5, so we can choose negative 3. Or if you're too lazy to figure out what that fraction is, just choose a giant negative number. Choose negative 1,000,000 for all I care. That's going to be a positive times, well, that'll be a negative if it's 2 times negative 1,000,000 plus 5. Yeah. And then 3 minus negative 1,000,000, that's going to be a positive. And positive, negative, positive is going to give us negative in the end. And that's all we need to do. Later on, once we've talked about what parabolas are, which are graphs of quadratic functions, then there's actually some more shortcuts that we could use for problems like the two of these. But if you're not comfortable with parabolas, then there's no sense talking about that now. And since we haven't officially discussed it as a class, I'm not going to get into it. But there are shortcuts. Let's look at something that's not quadratic, though. So we want to draw a sign diagram for this thing. If we've got a fraction, we want to think about the numerator separately from the denominator. Because the numerator is going to tell us when the function's equal to 0, and the denominator is going to tell us when it's undefined, because we can't divide by a 0. So what value is going to get us 0 in this case? Well, clearly x equals 1, because then I'll have 0 in the numerator. What value is going to make this thing undefined? It's going to be x equals negative 1/2, because that would give us 0 in the denominator. So our sign diagram is going to have those two values listed, and then we play the same game. Choose any value bigger than 1. They chose a pretty big one here. They chose x equal to 10. That's going to get you a positive in the numerator. 10 minus 1 is clearly positive. And it's going to get you a positive number in the denominator. I don't care that it's 9 over 21. That's totally irrelevant. It's just a positive number. So we can put a plus there. We put in 0 in between the two. That's going to get us a negative divided by a positive, which is negative. And then we choose something less than negative 1/2. Again, like negative 1,000,000,000. We're going to have a negative in the numerator, and we're also going to have a negative in the denominator, so that will make it positive. There's a note here from where I took this from that says, since each of these factors are single factors, the signs alternate, meaning it wasn't x minus 1 squared or cubed or something like that, that the signs here would alternate. That has to do with something called multiplicity, and we're absolutely not talking about that in this course. You can worry about that in the future. For our purposes, we're just going to choose our test points. We're not going to try to use any shortcuts with repeated factors. If you want to learn that on your own, great, but I'm not going to require that you know it, and I'm not going to discuss that any further. So the next thing I want to get into is verbally describing when a function is increasing or decreasing. And I think it's important to just get this vocab out there before we go any further. This might be obvious to you, but positive is not the same as increasing. Negative is not the same as decreasing. So the question here, which I forgot to copy onto the slide, is for this graph, y equals x squared, where is the function decreasing and where is the function increasing? Well, it looks like it's decreasing, meaning it's going down from left to right everywhere up until we get to the origin. And then it's increasing, again, it's going up as we move from left to right, everywhere to the right of 0. The function is positive everywhere except for 0. So its sign diagram would look like that. But it's decreasing to the left of 0, and it's increasing to the right of 0. There's a natural question to be asked here. The answer says that it's decreasing for x less than or equal to 0, and it says increasing for x greater than or equal to 0, which means that at x equals to 0, this function is both decreasing and increasing. How is that possible? We're not going to get into it. This is really a great question in a calculus course. Truthfully, as far as I'm concerned, if you said less than and greater than or mix and match, I don't really care. I don't think that should be our focus here. So don't worry about what happens when the graph is flattened out. Is the function increasing or decreasing there? Is it both? Is it neither? That's not a conversation for us to have. As I said in the intro, the point at which a graph changes from decreasing to increasing or increasing to decreasing is a special point called the turning point of the graph. In this case, that point would be a minimum, right? Because it's the lowest point. Graphs can have multiple minima and multiple maxima of varying types. So looking at a few examples here in diagram A, we see two local minima. What I mean when I say local is if I just zoom in close to that point, that's a minimum. So that's a minimum close by. That's another minimum close by. This one here is also known as an absolute minimum because it is the lowest of all the minima. Okay, so you can only have one absolute minimum or absolute maximum. You could have multiple local minima or maxima. Now, why is it that this point is only labeled a local maximum as opposed to a absolute maximum? Well, it's because the graph keeps on going up, both to the left and to the right. So there are plenty of points that are above that local maximum, so it's not an absolute maximum. This graph, in fact, does not have an absolute maximum because it keeps going up forever. We don't see the arrows there, but we can infer that they're there. In this diagram B over here, we've actually got endpoints for our function. So even though the function really goes on forever, we're only interested at what's happening in between that point and that point. So the deal with the minima is still the same. These are both local mins. This is also an absolute minimum. We still have a local maximum here. However, we have an absolute maximum at an endpoint. I think this probably sounds harder than it is. It's just that we have a lot of new vocabulary to deal with. Okay, so let's say that I had the function x to the fifth minus 4x cubed. I could do a few different things with it. First of all, I could make a sign diagram. It seems like I have zeros here at -2, 0, and +2. And just from looking at the graph, I can see that the sign is changing from minus to plus to minus to plus. I could also then answer, where is the function increasing and decreasing? As I start all the way at the left, it appears to be increasing from, well, from negative infinity, right? Because it's as we go out to the left, the thing's going down, right? So as I move to the right, which is how we need to think about this, therefore it is increasing all the way until we reach that local maximum, which is going to be just the x value, -1.5. Let's just call it -1.55. I can write my interval using rounded brackets or with square brackets. Actually, I prefer the square brackets. Oh no, there we go, 1.55. And again, I don't care if 1.55 is included or not, as I said earlier. Where else is it increasing? It's also increasing from 1.55 positive all the way to infinity. Where is it decreasing? Well, it's decreasing in between those 2 points, right? So it's going to be decreasing from negative 1.55 to positive 1.55. I could then finally answer where are the local maxima and minima. Clearly, there's a local max here at x equals negative 1.55. That's literally the point where it changed from increasing to decreasing. And then there's a local min here where we changed from decreasing to increasing. So increasing and decreasing and finding maxima and minima are intimately related. Sign diagram is separate from that, but they all fall under the general topic of describing the behavior of a function. So now the last thing that we need to talk about is, if I gave you this function but I didn't give you the graph, how are we going to come up with these values? We got to use our calculator, right? So we can graph the function, and then if we wanted to draw the sign diagram, we can go to Analyze Graph, calculate 0, lower bound, drag it over, upper bound. That gets us one of the zeros, and then we can repeat that for the other 2 zeros. In this case, they were integers, so we probably could have guessed and gotten away with it, but if they were decimals, that's how we'd want to do that. And for the min and the max, we're going to go to Analyze Graph and then choose either min or max. If I choose the max, that means I want to find this one, so I'll go to the left of it, click, drag over, right of it. There's my maximum. When I choose minimum, I can find that point. So these special points, the minima, the maxima, the zeros, are easy to find on our calculators. This is all important to note because as we move further into this course, we're going to have to graph more and more complicated functions. And when we transfer that information from technology onto paper, we want to include the important points. Any place where we have a max or a min, and any place where we're crossing the x-axis are definitely going to be important points that we're going to want to include in our sketch, along with horizontal or vertical asymptotes and other things that we'll worry about later on. Some things that we'll talk about in this course, some things that we won't talk about until future math courses. So that concludes this video lesson, which is just us taking further steps towards the ultimate goal of being able to analyze various functions and just be able to communicate all the important information about a function that we possibly can. Previously, we've talked about the domain and range of a function. That's very important information. Today we discussed sign diagrams, so where a function is above and below the x-axis, and then also where the function is increasing and decreasing, tied together with where it's changing direction. In the next video, we'll look at various types of discontinuities. Today we just said, oh, if there's a discontinuity, we'll say that it's undefined on the sign diagram, but there's actually different ways that a function can be discontinuous. And we'll also talk about what exactly should we say when the function is heading off towards positive or negative infinity. And then when we're done with all this, we'll take some time to put these various ideas together into some really fun function analysis. Because you can't spell function without a little fun, am I right? Woo!